Welcome to Summarize Science. Today, we're looking at a fascinating study about thoracic aortic aneurysms, which are dangerous bulges in the main artery coming from the heart. Currently, a doctor's main tool for assessing the risk of a rupture is the size of the aneurysm. However, we know that this method is imperfect, as some smaller aneurysms can be deadly while larger ones remain stable. The real risk often lies in the underlying microscopic problems within the aortic wall, like weakened elastic fibers or cells that don't properly sense stress. But these factors can't be seen directly in a patient, creating a major diagnostic challenge. To tackle this, researchers built a powerful computer simulation to generate hundreds of synthetic or virtual aneurysms. They started with a healthy aorta and introduced different combinations of these hidden problems. For each resulting virtual aneurysm, they generated two key pieces of information: a map of its shape, called dilatation, and a map of its stretchiness, as it pulses, called distensibility. They then fed these shape and stretchiness maps into several different types of artificial intelligence. The goal was to train the AI to work backwards, to look at the maps and accurately predict the specific hidden problems that caused that particular aneurysm. This is where it gets really interesting. The researchers tested the AI under two conditions: one where it only saw the shape data, mimicking the current clinical standard, and another where it saw both the shape and the stretchiness data. As you can see from these charts, the results were dramatic. The prediction errors, represented by the height of these bars, were significantly lower when the AI had access to both pieces of information. Let's look at an example. Here on the left is the ground truth of what's wrong with the virtual artery wall. The AI's prediction using only shape data is in the middle column. It's decent but flawed. But on the right, when the AI was also given the stretchiness data, its prediction is nearly a perfect match. The study also found that out of all the AI architectures they tested, a model called UNet was the most accurate and consistent performer. It did the best job at identifying the magnitude and location of the underlying problems. So, let's quickly recap what this all means. First, we've confirmed that just looking at the size or shape of an aneurysm provides an incomplete picture of its true danger. Second, measuring how the aneurysm stretches and recoils, its distensibility, provides vital clues about the hidden mechanical and biological failures driving its growth. And third, AI networks like UNet are powerful tools that can decode this complex information to give us a much clearer diagnosis. While this study used simulated data, it creates a roadmap for the future of patient care. Imagine a quick, non-invasive scan that captures both the shape and the mechanical behavior of a person's aorta. This data could be fed into a pre-trained AI, giving doctors an unprecedented look into the specific causes of that individual's aneurysm. This would allow for truly personalized treatment, helping to predict risk more accurately and potentially saving many lives.